In this session, we are going to talk about some elementary functions, and these are complex exponential function, complex logarithmic function, complex exponents or powers, complex trigonometric function, and complex hyperbolic functions. The examples are given here. Complex exponential function can be f of z equals e to the z. Logarithmic functions are log z, natural log z. Exponential functions are e to the z, but here complex exponents are z power alpha, where alpha is a non-zero complex number. So this is the example of complex exponent. Complex trigonometric functions can be sine of z, cosine of z, tangent of z, like this. Hyperbolic functions are hyperbolic sine of z, hyperbolic cosine of z. So we will try to discuss these topics in this session. Besides this, we have to know how we can define single valued function and multiple valued function. So remember, whenever we have multiple valued functions, at that time we will see some terms. These are known as branch, branch point, branch cut, or line. So these three terms are only applicable for multiple valued function. These are not applicable for single valued functions. So whenever we have multiple valued functions, only at that time we can think about branch, branch point, and branch cut or line. So besides this, we have to know how to find derivatives of these elementary functions. So since single valued and multiple valued are mentioned here, so I need to mention that complex exponential functions are always single valued function. Complex logarithmic functions are multiple valued functions. Complex exponents or powers are also multiple valued functions, but complex trigonometric and hyperbolic functions can be single valued functions. So complex exponential, trigonometric, and hyperbolic are single valued functions, and complex logarithmic and exponents are multiple valued functions. So before starting our main discussion, we have to recall whatever we have learned from our previous lessons. So we know that any complex number z equals x plus yi. So this is the rectangular form. And this same complex number can be written in polar form, r e to the I theta, where r is the modulus and theta is the argument. So we know that r equals square root of x squared plus y squared, which is also written as modulus of z, and the argument theta equals tan inverse y over x. So this argument can take multiple values. That means we will get many values. We can come from counterclockwise or from clockwise direction. That means in every rotation we will get new arguments. So that's why this ARG, where A is a small letter, so this defines a set of arguments. That's why we know that argument equals theta plus 2k pi. It actually doesn't matter whether we apply k or n. Instead of k, we can also say we have n. So theta equals theta plus 2n pi, where n equals 0, plus minus 1, plus minus 2, anything. Plus denotes the counterclockwise direction and minus denotes the clockwise direction. So this time with this formula, I need to mention another thing here, that the left side quantity that we have, it is the argument arg of set, small letter a, but on right side we have argument plus 2 and pi. So from now you have to understand that this argument is the principal argument. So principal argument always lies in between minus 180 degree to 180 degree. It can also be equal to 180 degree. That means capital A R G of Z lies in between negative 180 degree to positive 180 degree. It can also be equal to 180 degree. So theta equals theta plus 2 and pi now can be written as argument of Z equals principal argument plus 2 and pi. So why we need principal argument? Because this time we are going to talk about multiple valued functions. So whenever we have to know multiple valued function, at that time principal argument is very important. So besides this one, we have to know this notation. We also know that if we have z equals x plus yi, then this x is called the real part of z, this y is called the imaginary part of z. We also know any function f of z can be written as w equals f of z, which is equal to u plus vi. So here z is the input, w is the output. So from here we can also think about u is the real part of this function, that is u equals real part of w, v is the imaginary part of w, that is v is the imaginary part of the main function. We need to know all these things here. We also know what is the Euler's identity, that is e to the I theta, that is cosine theta plus I sine theta. We have another identity, e to the minus I theta equals cosine theta minus I sine theta. Similarly, we can think, suppose we have y instead of theta, so e to the iy equals cosine y plus I sine y. So from this concept, the main term that we have to know is how to find principal argument of any complex number. So we will discuss later. Now let's talk about how we can understand whether a function is single valued or multiple valued. So let's say any function is defined like w equals f of z, where z is the input and w is the output. So we have taken two sets. First one is for input z and the second one is for the output w. So we will ask ourselves how many values of w or f of z we have for any single input z. So let's say we have an input z1. We are inputting z1 here. So the output will be w1. So this time, if for this single input we will get single output, that means number of output is 1, then we can say the function that we have is a single valued function. That means if we ask how many values of w we have only one value of w for this z1. Let's say we have another point z2. For this input we have output w2, but for this input how many output we have? We have one output. So that means for every input, if we have one output, we can say that function is a single valued function. Similarly, we can think about multiple valued function. So let's say we have input z1. So if for this single input we get more than one output, that means say we have w1, w2, w3. So we have three outputs for this single input. That means if we have more than one output, then that function will be multiple valued function. But here for z1 we have only one output. But here for z1 we have three outputs. We may have four outputs. We have, let's say, five outputs, six outputs, many outputs. So that means if a function follows this pattern, then this function will be multiple valued function. That means if we ask ourselves how many values of w or f of z we have for this single input, we have more than one output. So this is multiple valued function. So one thing we need to mention here, that any single valued function is analytic, but multiple valued functions are not analytic but can be made analytic. So we have to understand that single valued functions are analytic, but multiple valued functions are not analytic but can be made analytic. So how can we make multiple valued functions analytic? The answer is, in multiple valued functions we may have several single valued functions, and we can say that single valued functions are analytic. So multiple valued functions are the collection of single valued functions. These single valued functions separately has name that we know as branch, but we will discuss this one later. So multiple valued function is a collection of many single valued functions. In my last session, I have discussed about analytic function. So you know that if we have a function w equals f of z that is equal to u plus vi, then if we check whether this function is analytic or not, then we need to have Cauchy-Riemann equations. So the Cauchy-Riemann equations in rectangular form are this, and the Cauchy-Riemann equations in polar form are defined by these two equations. So a function will be analytic if these two equations are satisfied. Similarly, if we take the polar form, the function will be analytic if we can satisfy these equations. So analytic function are differentiable. That means whenever we have discussed the definition of analytic function, we have mentioned that analytic functions are differentiable. So just now we have learned that analytic functions are single valued. So single valued functions are analytic and differentiable. That means we can find the derivatives. If we have f of z, we can find the derivative f prime of z. So if anyhow we can show whether a function is analytic or not, suppose the function is analytic, then we can find its derivative. So the formula for finding derivative is f prime of z equals du dx plus I dv dx. Or we can apply this formula, but we can apply this formula always if we take the rectangular form. Similarly, suppose a function is defined in r theta, that means in polar form, then we have the Cauchy-Riemann equations. So if we need to find the derivative f prime of z, then it can be defined by e to the minus I theta times du dr plus I dv dr. So here du dx, dv dx or du dr, dv dr are coming from Cauchy-Riemann equations. That means first we have to find all this, then we can evaluate the derivative of the function. So now we have to recall how we can find principal argument. So you know that principal argument is defined by capital A Rg of z. So this principal argument has a restriction. It is in between minus 180 degree to 180 degree, but it can also be equal to 180 degree. So for example, I have mentioned here 4 examples. So we need to find principal argument of these 4 examples. So we have z equals 1 plus I as the first complex number, minus 1 plus I second complex number, minus 1 minus I as the third complex number, 1 minus I as the fourth complex number. So we have 4 complex numbers in 4 different quadrants. This one is in first quadrant, this is in second quadrant, it is in third quadrant, it is in fourth quadrant. So if we can understand the location of any complex number, so we can easily find the principal argument. This time we are asking for principal argument, not argument, ARG. We are asking for capital A, RG. So here we can see that for this point, that means if we have a point in first quadrant, we can see the angle will be in between 0 degree and 90 degree. So we have found 45 degree. Yeah, that is okay. But we have to check whether it is principal argument or not. Yeah, 45 degree is in between minus 180 degree to 180 degree or equal to 180 degree. So that means 45 degree is the principal argument. That means whenever we are using this formula, if a point is in first quadrant, the result we are getting from this formula is denoting the principal argument. Similarly, if we have a point on fourth quadrant, by using this formula, we are getting a result. So that result will be also principal argument. So if we have a point in first quadrant or in fourth quadrant, this formula will give us directly principal argument. But if we have a point in second quadrant, then we can apply the formula tan inverse y over x. So tan inverse minus 1, that is minus 45 degree. So minus 45 degree is in between this region, but that is not the correct result. We can see that the argument can be in between 90 degree to 180 degree. So this time we have to add 180 degree with this result. That means we have 135 degree. So this is now principal argument. So 135 degree is in between this region. Similarly, if we have a point in third quadrant, we can think about coming from counterclockwise to that line. But if we come from counterclockwise, then it is now greater than 180 degree. So that will not be our principal argument. That will be just argument, but not principal argument. So we have to come from negative direction. So in negative direction, we can easily understand that we have a result that is in between negative 90 degree to negative 180 degree. But by using this formula, we are getting only 45 degree. We are getting this result. So we have to adjust to get the principal argument. That means this time we should add negative 180 degree with this result. So that means it will be negative 135 degree. Now this is principal argument. So minus 135 degree is in between this region. So remember, principal argument is always unique. For a complex number, we will have only one principal argument. But argument can be a set of values. But if we ask for principal argument, then it will be unique. So from now, you can find a pattern. A complex number may be in first quadrant, second quadrant, third quadrant, fourth quadrant. If a complex number is in first quadrant or fourth quadrant, then the formula that we have for argument will give us a result, and that result will definitely be the principal argument. We don't need to adjust anything. But if the point is in second quadrant, then the result we are getting from this formula will not be accurate. So for second quadrant, we have to add 180 degree with this result. Then we will get the principal argument. If the point is in third quadrant, at that time, again, we have to adjust, because from the formula, we are not getting the exact result. So that's why, remember, whenever we have third quadrant, then we have to add negative 180 degree with the result. Then you will get the principal argument. So for second quadrant, add plus 180 degree. For third quadrant, add minus 180 degree. So this is how we can find principal argument. And we will discuss about principal argument later, whenever we will talk about multiple valued functions. But before, you have to know how we can find principal argument. So this time, let's talk about complex exponential functions. So we have so many functions to discuss, but first we have to talk about complex exponential functions. So complex exponential functions are e to the z. F of z equals e to the z. Complex exponential functions are single valued. So let us define complex exponential function. So suppose we have w equals f of z equals e to the z. So complex exponential functions are e to the z. So we have mentioned that complex exponential functions are single valued. Now we can think about z as x plus yi. So we can write e to the x times e to the yi. So we have w equals this one. That means w equals e to the x times e to the iy. That is e to the yi and e to the iy are same. So now we are going to apply Euler's identity. E to the iy is cosine y plus I sine y. So we have e to the x cosine y plus I e to the x sine y. This is w. So we know that any complex number w equals f of z can be written as u plus vi. So we have found u plus vi. So here u is e to the x cosine y, v is e to the x sine y. So we know that complex exponential functions are single valued. So all single valued functions are analytic. We have also mentioned this earlier. So we can understand that f of z equals e to the z is analytic. And in my last session, I have shown that f of z equals e to the z is analytic. Okay, that means we have shown Cauchy-Riemann equations are satisfied for this equation. So we can say complex exponential function f of z equals e to the z is analytic and single valued. So if a function is analytic, that function will be differentiable. So from our last session, we have du dx equals this one, du dy equals this, dv dx, dv dy. So since e to the z is analytic, that means e to the z is single valued and e to the z is differentiable. That means f of z is differentiable. So if f of z is differentiable, then we can find f prime of z. So we are going to evaluate the derivative of e to the z. ddz of e to the z will be what? We can think about real valued derivative. We know ddx of e to the x equals e to the x. Similarly, we will get the same result here. ddz of e to the z will be e to the z. But how? So the answer can be given from this formula. If a function is analytic, we can say the function is satisfying the Cauchy-Riemann equations. That means the function is analytic and therefore the function is differentiable. So for differentiable criteria, we have this formula. That means if we need to find the first derivative, f prime of z, that can be found by this way: du dx plus I dv dx. So our target is to find the derivative of e to the z, that is d dz of e to the z, or f prime of z. So since we have this formula is found from analytic function. That means the function is analytic, and so we are using this formula. So f prime of z equals du dx plus I dv dx. So du dx, we have the result. It is e to the x cosine y plus I dv dx. It is e to the x sine y. So we can just factor out e to the x. We have cosine y plus I sine y. So that means e to the x. Now Euler's identity says that cosine y plus I sine y will be e to the iy. So we can write e to the x plus iy from this equation. So we know that x plus yi is z. That means we have found our result. That is f prime of z is e to the z. So derivative of e to the z equals e to the z. So in complex analysis, if we have to find the derivative of any function, that function should be single valued and analytic. If we have analyticity criteria, then only we can find the first derivative. So now we have established that d dz of e to the z equals e to the z, or if f of z equals e to the z, then f prime of z is e to the z. So let's have a look on the properties of exponential function. So we know e to the 0 is 1, e to the z1 times e to the z2 equals e to the z1 plus z2. We have applied this property here. E to the x times e to the iy is written as e to the x plus y I. Similarly, if we have e to the z1 by z2, we can write e to the z1 negative z2. And lastly, e to the z power n can be written as e to the n z, where n is any integer. Besides these algebraic properties, exponential functions are also periodic. It has a period of 2 pi I. Actually, we can generalize the term. 2 pi I can be 2n pi I, where n is any integer. N can be 0, 1, 2, 3, minus 1, minus 2, minus 3, and so on. So, what is the meaning of periodicity? Suppose we have e to the z. Instead of z, we are plugging z plus 2 pi I. So, whenever we are plugging z plus 2 pi I, we are getting the same function back. So, this is called periodic function. So, we can verify this one. That is, if we have e to the z plus 2 pi I, we can write e to the z times e to the 2 pi I by using second property. Then we have e to the 2 pi I as e to the I 2 pi. So e to the I theta. By using Euler's identity, we can write cosine theta plus I sine theta. So we know that cosine 2 pi, cosine 360 degree is 1, sine 360 degree is 0. So we have e to the z times 1 plus I times 0. So this part is vanished. We have e to the z. So that means complex exponential functions are periodic. Similarly, we can think about n equals, let's say, 2. So 2 times 2, 4. So if we add z plus 4 pi I, we will get e to the z back. And same thing holds for n equals 2, n equals 3, n equals minus 1, minus 2, minus 3, like that. So up to now, we have checked how to find the derivative of e to the z. And we have mentioned that e to the z, that is exponential functions, are single valued functions. So let's have a look on some examples, or let's say one example from where we can understand that yes, complex exponential functions are single valued. So let's say we have a function f of z equals e to the z, which is the exponential function. Let's say this is w. So suppose we are going to input any complex number. Let's say this is our input and this is output. Input is denoted as z, output is denoted as w. So suppose we are going to input any complex number, 2 plus pi I over 4. So let's see what happens for this input. If we get more than one outputs, then this function will not be single valued, it will be multi-valued. But if we get one output only, then it will be single valued functions. And definitely complex exponential functions are single valued. So let's input z equals 2 plus pi I over 4. So here we can write 2 over 4 plus pi over 4I. So e to the 1 by 2 plus pi over 4 I. So we know that e to the z1 plus z2 can be written as e to the z1 times e to the z2. So e to the 1 by 2 is same as square root of e. E to the I theta, it is cosine theta plus I sine theta. It is by Euler's identity. And don't forget that in left side we have w. So w equals root over e cosine pi over 4, that means cosine 45 degree is 1 over a square root of 2 plus I sine 45 degree sine pi over 4 is 1 over root 2. So we can factor out 1 over root 2. We have 1 plus I. So that means square root of e over 2, 1 plus I. We have found our output. We can evaluate the numerical value of this. That will take a form u plus vi, but that is of no need. The main point is that how many values of w we have found for this input. We have found only one w. We have found only this one. Our output is 1. So that means e to the z is always single valued function. So we have square root of e over 2, 1 plus I. We have found one output. So we can say that e to the z is single valued function. So since we are dealing with exponential functions, we can solve some problems. Let's say we have to solve e to the z equals 1 plus square root of 3i. So for solving this equation, what we have to do, we have to input z as x plus y I, and on the right side we have a complex number that can be converted to polar form. But first try to understand the question, that we have to find the values of z. We need to solve this equation. That means the alternate form of the question will be find all the values of z for which we have this result. So remember one thing, that e to the z is a function. E to the z is an exponential function, and we have mentioned several times that e to the z is always single valued function. So for e to the z we have this single output. How many output we have? We have only one output, 1 plus root over 3i. But for what values of z we have this output? We need to find. So this z can be many values. Let's see what happens. That means this time we have so many values of z. This jet has an output, this one. This jet has an output, the same one. This jet has an output 1 plus square root of 3i. So for every input, how many output we are getting? 1. For this input, we are getting this output. For this input, we are getting 1 output. For this input, we are getting 1 output. So we can say that complex exponential functions are single valued. So this jet can take many values, but the output will be only one value. That is already given, 1 plus square root of 3i. So let's solve this one. We have e to the z equals 1 plus square root of 3i. So for solving this, we need to input z as x plus yi. So we have e to the x plus yi, 1 plus square root of 3i. So the right side complex number is in rectangular form. We can convert this to polar form, r e to the I theta. So that means for this complex number, we have to find r and theta. We are targeting for z. That means finally z will take the form x plus y I. We need to find x and y first, then we can construct z. So this is our target. So here 1 plus square root of 3i is given. So r will be x squared plus y squared square root. That means 1 squared plus root over 3 squared square root. So we have 1 plus 3 root over 4. That means 2. R is 2. And let's look at this point. 1 plus square root of 3i is nothing but 1 comma square root of 3. That means it is in first quadrant. So whenever a point is in first quadrant or fourth quadrant, the angle that we get from tan inverse y over x will be accurate. We don't need to adjust this one. That means this will be the principal argument. So we need to find always the principal argument. So inverse tan of square root of 3 over 1, that means tan inverse square root of 3, it will be 60 degree. So we know that 60 degree is pi over 3. That is, if 1 degree equals pi over 180 radian, then 60 degree will be 60 pi by 180 radian. That means pi over 3. So we have found r equals 2 and theta, that is principal argument, as pi over 3. So in left side, we can use the property e to the x times e to the yi. On right side, we can input the value of r and theta. So remember one thing, that argument equals argument plus 2n pi. This argument is the principal argument. So argument can take many values, but principal argument will be only a unique value. This n equals 0, plus minus 1, plus minus 2, and so on. So we can understand that theta equals theta plus 2n pi. So here we have this equation. So from this we need to find x and y first, then we can construct z. That means we can find the values of z. So here this part is the modulus and this part is the argument. Similarly, on left side we can think about this is the modulus and this is the argument. So let me write in a convenient form. We have I, y. So since this is the modulus, this will be also the modulus. E to the I theta, e to the I y. So this is the argument. So that means we have this equation. So this is a complex number, this is another complex number. So two complex numbers are equal if their modulus are equal and their arguments are equal. So we can say that modulus are equal and arguments are equal. So this is the modulus for the left side, r e to the I theta. So this is obviously the modulus. Similarly here r e to the I theta. So this is the modulus. So we can write e to the x equals 2 and y equals pi over 3. So I hope you have understood how to find these two equations from this equation. We are collecting the modulus from two sides and we are collecting the arguments. So here this argument pi over 3 is the principal argument. That means it is pi over 3, and we know that any argument can be principal argument plus 2n pi. So that means we can say theta equals theta plus 2n pi. So where we have theta, we can input theta plus 2n pi. So we have e to the x equals 2 and y equals pi over 3. So besides this, we are adding 2n pi. So remember, n equals 0, plus minus 1, plus minus 2, up to infinity. So our target is to find x and y because we need to have z finally. Let's find x. So for finding x, we can take natural log on both sides. So natural log of e to the x equals natural log of 2. So we have to know one property, that natural log of e power x is equal to x. So how we can find this one? We can think about this way, that we know that if we have log a power b, then we can write b log a. So log a power b, we can write b log a. So Natural log of e is 1. So x times 1, that is x. So that means this natural log of e to the x is working as real log. That means real logarithmic function. It is not complex logarithmic function. It is real logarithmic function since it is coming from modulus. So modulus is always a real number. Modulus r, that is modulus of z, is always greater than 0 and real number. So we can write natural log of e to the x as x equals natural log of 2. So we have found x and we have y. So our target is to evaluate z. So z equals, we know, x plus yi. So this is the time to input x and y. Y is pi over 3 plus 2n pi I. So this is our z. So we have many solutions of z where n is 0, plus minus 1, plus minus 2, up to so on. This is our result. That means this is how we can solve these equations. So let's have a look on the process again. At first, we have plugged x plus y I in the left side, and the right side complex number has been converted to the modulus and e to the I theta, that is r e to the I theta. So it has been converted to the polar form. Then we have two complex numbers in left side and right side. So these two complex numbers are equal. That means their modulus are equal and their arguments are equal. So we know that theta equals theta plus 2n pi. So we have used theta plus 2n pi. Then for finding x, we have taken logarithm on both sides. And finally, we have x and y. Where we have z, let's input x and y. So we will get the result. So this is about complex exponential function. And now let's talk about complex logarithmic function. So complex logarithmic functions are multi-valued functions. That is multiple valued functions. So since multiple valued functions are dealing with branch point, and branch cut, so we will try to discuss this time branch, and later on we will try to discuss branch point and branch cut. So let's talk about complex logarithmic function. So complex logarithmic function comes from the equation e to the w equals z. So complex logarithmic function is a function which can also be thought to be w equals f of z. So just now we have seen if we have e to the x equals 2, we have taken natural log on both sides to get x. So similarly, from this equation, we have to find w. So we are taking log on both sides. So natural log of e to the x equals x. That means natural log of e to the w is equal to w. So this is equal to natural log of z. So that means this is our f of z. So we can say that w equals f of z equals natural log of z. Just like exponential function, w equals f of z equals e to the z, we have the logarithmic function, complex logarithmic function. So here we need to also understand the alternative notations of complex logarithm, because in some textbook natural log of z is written as log z. Here we have a small letter l. So this is also complex logarithmic function. Just like argument and principal argument, we can think about complex logarithm and principal complex logarithm, that is principal value of complex logarithm. So here we have a small letter l, here we have capital letter L. So since this is principal value of complex logarithm, that means it is obviously coming from principal argument. So this is also f of z. Just like a small l og, we have written capital Log, that is the principal value of complex logarithm. Similarly, we have natural log of z, small l. We can think about w equals f of z, that is capital L n of z. So we have all these notations which are known as complex logarithm. So let us define complex logarithm. So just like this example, here we have e to the z 1 plus the square root of 3i. The process that we have followed here, we will follow the same process to solve this equation. So let's say we have again e to the w equals z. So we know that w equals u plus vi. So let's plug u plus vi, and on the right side let's convert this number to the polar form. We are using the same pattern as this problem. In left side we are plugging x plus yi, that means we have z, and the right side is converted to the polar form. So we are following the same pattern. And then we have e to the u times e to the vi r e to the I theta. So this is r e to the I theta. Let's write in convenient form IV. It is also r e to the I theta. So two complex numbers are equal if their modulus are equal. So we can say e to the u equals r, and their arguments are equal. So v equals theta. This theta is the principal argument of z. So here you have e to the u equals r and v equals theta. So theta can be written as theta plus 2n pi, where n equals 0, plus minus 1, plus minus 2, and so on. So in previous problem, our target is to find z. Here our target is to find W. So W equal to U plus VI. So we need to find first U and V. Already V is in our hand. So in this equation, we are taking natural log. So natural log of e to the U equals natural log of R. So from here, we can directly write this is U and this is natural log of R. So U and V. So that means we can say W equals U plus VI. So U is natural log of R, V is theta plus 2n pi I. So this is our complex logarithm. We have already established that W equal to log z, natural log z. We have these notations. So we can say this W equals f of z, which is log z. So log z equals this quantity. We have to focus on the right side. We don't need to focus on the left side. In left side, we have natural log of z. That means we have f of z. This is the main thing. But right side is the main concept. We have natural log of r plus argument, which is the principal argument, plus 2n pi. So we can define complex logarithm in this way, that is log z equals natural log of r plus theta plus 2n pi I. So this is f of z, which is equal to this one. Here we can also write this one as log z equals natural log of r plus argument of z plus 2n pi I, where n equals 0, plus minus 1, plus minus 2, up to infinity. So instead of this notation, I will use this one. Instead of this notation, I will use this one for this session. But you have to remember that all these notations are alternative form. This and these are alternative. This and these are alternative. So here we can see that the complex logarithm log z equals natural log of r plus argument of z plus 2n pi I. This is the principal argument. So we know that complex logarithmic function are multiple valued function. That means we have many outputs. So let's check whether it has many outputs or not. If we input n equals 0, then we have log z equals natural log of r plus argument of z plus 0 I. So we have log z plus natural log of r plus argument of z I. So that means we have found one output. If we input n equals 1, then log z equals natural log of r plus argument of z plus n is 1, so 2 pi I. So this time we can see that the result that we have found here, it is not same as this one. We have extra 2 pi here. So that means this output and this output are not same. So we can understand that complex logarithm has many outputs. So that's why complex logarithm is multiple valued function. But this and this are separately single valued function. So remember, whenever we are plugging n equals 0, then this log becomes principal log. So principal value of complex logarithm will be evaluated if we plug n equals 0, because at that time this part is vanished. We have only principal argument and nothing is there. So that's why the log that is found for only principal argument is the principal value of complex logarithm, which is denoted by capital L O G of z. So we can say that complex logarithm is a multiple valued function. So this time I am going to define branch. So for n equals 0, we have found a log. We have found this result. For n equals 1, we have found another result, this one. Similarly, for n equals 2, we will get another log. For n equals 3, we will get another log, and this process will be continued. Therefore, we can say complex logarithm is multiple valued function. But this log is a single value. That means here we don't have any n. Similarly, in this part we don't have any n. So that means this is another single value. This is another single value. This is another single value. So multiple valued functions are collections of single valued functions. So all single valued functions collectively form multiple valued function. Now all these single valued functions are called branch. So for n equal to 0, the result that we will find, that is a branch. For n equals 1, we have a log, which is a single valued function, that is a branch. Similarly, we have many branches. You can remember that when n equals 0, then this log becomes capital log. So log, capital L. So that means I have mentioned that this defines the principal value of the complex logarithm. So it is true that This is a branch, but since it has a specific name, principal value of complex logarithm, capital L, so we can say that this branch is called the principal branch. So what is branch? Branch is the single valued functions that are coming from multiple valued function. Now let's talk about branch point. So for our convenience, we are writing log z. So any complex number z that is equal to x plus y I and w equals u plus vi. We know this one. So for this complex logarithm, if we need to find branch point, then we can think about another way. This z is z negative 0. So in general, if we have a log of z negative a, then we can solve z negative a equals 0. We will get z equals a. So z equals a is a branch point. So that means if we have log z, so instead of z, we can write z negative 0. And if we solve z negative 0 equals 0, we will get z equals 0. So z equals 0 is a branch point of complex logarithm. So complex logarithm of z means complex logarithm of z negative 0. That means z equals 0 is a branch point. We can define branch point in another way. Branch point is the point that can be a center of a circle. So say we have this circle. So if we rotate around this circle, then we will come from branch 1 to the second branch. If we take another rotation, we will come to another branch. If we take another rotation, we will come to another branch. That means it is working with n equals 0, 1, 2, 3. N equals 0 means there is no rotation. That means we have the principal branch. N equals 1 means we have made one rotation and found another new branch. N equals 2, that means we have made another rotation and we have reached to another branch. So n equals 3 means we have made another rotation and we have found another branch. All these branches are totally different from one another. So by using the concept of branch point, which is working as a center of a circle, we have found different branches. That means we are getting multiple valued functions. So we know that multiple valued functions are not analytic, but it can be made analytic because previously we have mentioned this concept. Multiple valued functions are not analytic but can be made analytic. But single valued functions are analytic. So using this concept, we can understand that all branches are single valued functions. Therefore, all branches are analytic. So from multiple valued functions, if we need an analytic function, then we have to restrict our domain so that we don't have all other branches. That means we have found this one, that is okay. So only if multiple valued functions are converted to single valued functions, then we can say that function is analytic. Otherwise, it is not. So multiple valued functions can be made analytic if we can find the single valued functions. So all single valued functions are analytic, but since multiple valued functions have different branches, so for every rotations we are getting different branches. That means we are getting again multiple valued, but this time we have to make a restriction so that from this branch we don't go anywhere. So that's why we need a cut, that is we need a branch cut. So branch cut works as an artificial barrier so that we may not have different branches. Suppose we need only this one but don't all these branches. So at that time we need branch cut. That means we need to restrict the argument. You can understand that if we have argument as principal argument plus 2n pi, that means we will have different branches. So we don't need to have this one, and it is only possible if we have a branch cut. So branch cut is up to our choice. We can take any line as branch cut, but branch cut will always be adjacent to the branch point. Let's say this is branch point and this is the branch cut. So branch cut is also known as branch line because it can be thought to be a line also. For now, let's try to understand that branches are known as all the single valued functions of a multiple valued function. Branch point is the point that is the center of a circle. So for complex logarithmic function log z, this can be written as log z minus 0. So z equals 0 will always be a branch point. But for log z minus a, we can say z equals a will be the branch point always. Let's say we have log z minus 1. So z equals 1 will be the branch point. So branch point means if we rotate along a circle where branch point is the center, we will get different branches with every rotation. But our target is to have an analytic function. Our target is to have only one single valued function. We don't need all branches. We need only one branch. Let's say we need this one. Or let's say we need this one. So what should we do? We need to have a restriction. That restriction is given by a term which is known as branch cut. This is just a line which is adjacent to the branch point. So whenever we have a branch cut, we need to understand that we have to come in such a way so that we don't cross this cut. Then only it is possible to have only a single function. Then only it is possible to avoid all branches. That means we will not make any rotation. Suppose we are starting from here, but we are not touching the starting point. So it will be just like this. We are starting from here and we are stopping here. So that means we don't have any complete rotation. If we don't have any complete rotation, then obviously there will be no other branches. So we are confined with this branch. So this is what we know as branch, branch point, and branch cut. So let's solve one problem from complex logarithmic function. Suppose we are going to evaluate log of 1 minus I. From here, we can also evaluate log of 1 minus I. So remember, this log means principal value of complex logarithm. And this one defines the general form. So we have to find log of 1 minus I. We can also think about in another way, that is solve e to the w equals 1 minus I. So I have written three different alternative question patterns here, but the process of answering is same. If we have a look on this one, we know that we can take natural log of both sides. So we have log e to the w equals w. So this is equal to natural log of 1 minus I. So we can say natural log of 1 minus I or log of 1 minus I are the same thing. From here, we can also find the principal log. So that's why you have to know all the alternative notations. So log of 1 minus I, natural log of 1 minus I are the same thing. All this defines w equals f of z. So for convenience, we are using this notation. So suppose we are going to evaluate log of 1 minus I. So we have already defined that any complex log can be written as natural log of r plus argument of z plus 2n pi. So this one, natural log of r, is acting as the real log. That means it is real logarithm. So let's evaluate this one. We have log 1 minus I. We know that log z equals natural log of r plus principal argument plus 2n pi I, where n equals 0, plus minus 1, plus minus 2, and so on. So we can compare that log z log 1 minus I. So that means z equals 1 minus I. So from here, we have to find modulus and principal argument. Log of 1 minus I equals natural log of r plus principal argument plus 2n pi I. So here z equals 1 minus I. So we can understand that we have to find r and theta. And that theta should be the principal argument. So first, let's find a point of this. It is 1, negative 1i. That is 1, negative 1. Let's look at the position of this point. 1 minus 1. That means it is in fourth quadrant. So we know that if a complex number is in first quadrant or fourth quadrant, then the formula that we know will give us the accurate result. So inverse tan of y over x, negative 1 over 1, we will get tan inverse negative 1, that is minus 45 degree. Yeah, that is correct. So minus 45 degree is the principal argument. We know principal argument lies in between 180 degree to 180 degree. It can also be equal to 180 degree. So minus 45 degree lies in between this region. So minus 45 degree is okay. That means minus pi over 4. So this is how we have found principal argument. The location is important. Also, we need to have r. So r equals x squared plus y squared, square root. So 1 squared plus minus 1 squared, that means the square root of 2. This is r. So now from this equation, we can write log of 1 minus I equals natural log of r. R is square root of 2 plus principal argument. Principal argument is negative pi over 4, this one, plus 2n pi I. So this is our result. And this is the complex log. That means we can say f of z equals natural log of root 2 plus minus pi over 4 plus 2n pi I. So this is our final result. We have found log of 1 minus I. That means this part is done. This part is also done. Same meaning. Now our target is to find the principal value of this log. That means we need to find capital Log, and this is only possible if n equals 0. So here we can understand that this log, this function is a multiple valued function, because if we input n equals 0, plus minus 1, plus minus 2, and so on, we will find different results, different outputs, and all outputs are known as branches. So we will have many branches. So for n equals 0, we can input, there will be a result. For n equals 1, we will get another result like this. So our target is to find the principal value of complex logarithm. So the principal value of the complex Logarithm is found by inputting n equals 0. So principal log can be found by inputting n equals 0 in this equation. That means let's input n equals 0 here. So if we input n equals 0, this log 1 minus I equals natural log of square root of 2 plus negative pi over 4 plus 2 times n is 0, so 0 I. So that means we are getting natural log of square root of 2 negative pi over 4 I. So since we have plugged n equals 0, that means this time we can write small l as capital L. So this is the principal value. This is known as principal branch also. This is a branch, but since we have n equals 0, we have the principal value of the complex logarithm, so we can define this one as principal branch. That's why we have established these definitions earlier, that the first branch is known as the principal branch. So if we want to find the branch point of this complex logarithmic function, we can think like this way. We have log z. So we know that if we have log z, this is log z minus 0. That means at z equals 0, there is a branch point. That means z equals 0 is known as a branch point. So log 1 minus I, that means this is our z, log z. So z equals 0 will be always a branch point. And for n equals 0, we have the first branch. For n equals 1, we have the second branch. For n equals 2, we have the third branch, and we can go forever. So we have the principal value of log. We know that this is f of z, that is w equals f of z. So we know w equals u plus vi. So we can see that this is u and this is v. So we can also find the numerical value of this if we want. We can use calculator for evaluating natural log of square root of 2 and also negative pi over 4 if we want. We can evaluate. So we have found the principal value of complex logarithm. That means we have found the principal branch. So out of all the multiple valued functions, we have found one single branch. This is a single valued function. We know that multiple valued functions are not analytic but can be made analytic. So it can be made analytic if we find single valued functions, like for n equals 0 we have this single valued function, for n equals 1 we have another single valued functions, like that. So From multiple valued functions, we have different branches, but all branches are single valued functions. So all single valued functions are analytic. So we can understand that complex logarithm is a multiple valued function. So just to make this complex logarithm analytic, we need to have any branch. Let's say we need to have a single branch. So first of all, what we can think about? We can think about inputting n equals 0. So if we input n equals 0, this small l will become capital L. So principal value of complex logarithm equals natural log of r plus principal argument n equals 0. That means this term is vanished. We have I. So this is the time when we can check whether this function is analytic or not. That means from this multiple valued function where n equals 0 plus minus 1 plus minus 2 like this. So this is a multiple valued function. From all these branches we have found a single branch. So since it is a single valued function, it must be analytic. So now we have to check whether it is analytic or not. So we know that any function can be written as w. So this is w equals f of z equals u plus vi. So here u equals natural log of r, v equals theta. So we have to check whether this function is analytic or not. Obviously, it will be analytic because we have restricted our domain. We didn't find all branches. We have found only one single branch here because we have no rotation. So this time the angle argument is in between minus pi to pi because we know that principal argument lies in between minus pi to pi. It can be equal to pi, but here we have this restriction. So suppose we are making a rotation around this branch point. We have to stop here. Otherwise, if we make a complete rotation, then we will get a different branch. So at that time, the function will not be analytic. So that's why there will be no rotation. That's why if this is the argument theta, so theta will be restricted from 0 degree to 2 pi. It is not equal to 2 pi. That means if we write equal, then it will touch this line. So there is a problem. We will get a different branch. So that's why we are not using equal sign here. So that's the reason why we have not written minus pi less than argument, that is principal argument less than equal to pi. But previously we have written principal argument as negative pi to positive pi, or it can be equal to pi, this one. Since we have made a restriction, we can say this will be a branch cut. We are cutting this part in such a way so that there will be no rotation. This is for 0 to 2 pi. But since we have minus pi to pi, we can think about the branch cut in this way. Minus pi to pi. So this is minus 180 degree to 180 degree. So this time this is a cut. So you don't need to think about branch cut or branch point. Our main target is to check whether this single valued function is analytic or not. So that means we have to verify whether the Cauchy-Riemann equations are satisfied or not. So we know there are two forms, rectangular and polar. So in polar form we have r and theta. So since we have r and theta here, so this time we have to use Cauchy-Riemann equations in polar form. So we know that Cauchy-Riemann equations in polar form are du dr equals 1 over r dv d theta, and dv dr equals negative 1 over r du d theta. So if these two equations are satisfied, then only we can say this function f of z, or principal value of complex logarithm, or this single value, or this w, is analytic. So you can see that we have to find du dr, du d theta. So let's find du dr. That means we are differentiating natural log of r in terms of r. We know ddx of natural log of x equals 1 over x. So it will be 1 over r. Similarly, du d theta, that means we are differentiating natural log of r. So we are using partial derivative concept. Whenever we are differentiating in terms of theta, r is constant. So that means derivative of constant is 0. Now we need to find dv d theta, dv dr. Let's find dv dr first. So we are differentiating theta in terms of r. That means we are differentiating in terms of r. So theta is constant. So derivative of constant is 0. Now let's similarly find dv d theta. So differentiation of theta in terms of theta. So differentiation of x in terms of x is 1. Similarly, differentiation of theta in terms of theta is 1. So we have found du dr as 1 over r, du d theta is 0, dv dr is 0, dv d theta is 1. So let's check whether these two equations are verified or not. So du dr, which is 1 over r, equals Cauchy-Riemann equation says that it will be 1 over r dv d theta. So that means 1 over r dv d theta is 1. So we have 1 over r equals 1 over r. That means the first equation is satisfied since these two values are same. Similarly, let's check the second one, dv dr. So dv dr is 0 and minus 1 over r du d theta. So du d theta is 0. So minus 1 over r times 0 is 0. So that means the second equation is also verified. So therefore, we can say that this complex logarithm, which is principal branch, which is the principal value of complex logarithm, is analytic. That's why if a multiple valued function is small log, that is log of z, if this has to be analytic, then it has to be converted to any single valued function. At that time, we have to restrict the angle. That's why we need a branch cut. So branch cut is a complicated term, but we can think like n equals 0, we are getting a term. For n equals 1, we will get another term. Then at that time, we will get another angle, another restriction. So we can say that any single valued function is analytic. So we have shown that f of z equals log z is analytic. So since it is analytic, it is differentiable. We have learned this concept earlier. If a function is analytic, if a single valued function is analytic, then it is differentiable, and we can apply this formula since we have used polar form to evaluate the first derivative. So you can understand why branch cut is important. Branch cut is important so that we have a single valued function from a multiple valued function. If you are having trouble with the term branch cut, then you can think about n equals 0 only, or n equals 1 only, or n equals 2 only. Okay? So f of z equals log z is analytic. That means this function is differentiable. So f prime of z equals e to the minus I theta du dr plus I dv dr. This is our formula. If a function is analytic, then f prime of z, that is first derivative, can be found by this way. So e to the minus I theta du dr. So our du dr is 1 over r plus I dv dr. dv dr is 0. So we can say this is 0. Now f prime of z equals e to the minus I theta times 1 over r. So this is written as e to the I theta in denominator because we can make it in reciprocal form. Now we know that z equals r e to the I theta. So r e to the I theta can be written as this. So f prime of z, that means d dz of log z is 1 over z. So just like differentiation of e to the x is e to the x, we have proved that d dz of e to the z is e to the z because e to the z is analytic and single valued. Similarly, we know d dx of natural log of x is 1 over x. Similarly, d dz of log z is 1 over z. So whenever we have started complex logarithmic function, at that time I have mentioned that we have to know all the alternative forms. We know that complex logarithmic functions can be written as this natural log of z or this log of z. Similarly, small ln of z, small log of z. So these are alternative notations. So that's why, since we have shown that d dz of log z is 1 over z, similarly we can write d dz of natural log of z is 1 over z. So that means the derivatives that we have learned from differential calculus for real valued function, in complex valued function we are getting the same derivative, d dx of e to the x e to the x. Similarly, in complex variable, d dz of e to the z is e to the z. We have learned in differential calculus that d dx of natural log of x is 1 over x. Similarly, now we have learned that d dz of natural log of z is 1 over z. But the proof is different. If we have to prove d dz of natural log of z is 1 over z, then at first we have to show this function to be analytic. So this function is analytic because it has been made a single valued function. We have taken n equals 0, and that's why we have found capital L O G of z. So that's why this function has become analytic. Similarly, if we take only another single valued complex logarithmic function, let's say for n equals 1, we'll get another log. So for that log, there will be a defined angle. There will be a defined branch cut. So for all single valued functions, we can say d dz of log z is 1 over z. That means this formula holds for all single valued function, all single valued branches. That's the thing. So we have discussed about complex logarithmic function. Let's have a look on complex exponents. So complex exponents are written as f of z equals z to the alpha or z to the c, where alpha or c is a non-zero complex number. So I have mentioned that these complex exponents are also multiple valued function. So complex exponents are multiple valued functions because in complex exponents we will get again the logarithmic function. So that's why it is again multiple valued function. So if we have to make it single valued function, we need only one branch by defining a specific angle. For n equals 0, we will get the principal branch like that. Then only we can find f prime of z. So let's talk about complex exponent. So complex exponents or complex powers are defined as f of z equals z to the alpha. We have to also know the alternative notation. In some textbook, we will see it is written as z to the c. So here, z is a non-zero complex number. Alpha or c is also another complex number. We can think about, let's say we have 1 plus I, this is z, and in power form, we have 1 negative I. So this is a complex number, this is another complex number. That's why this function is known as complex exponent. The exponent or power that we have, that is also a complex number. So whenever we have f of z equals z to the alpha, so I am working with z to the alpha. So we can say that any function w equals f of z. So in that sense, we can write w equals z to the alpha. So we have to understand that complex exponent is defined by a formula. That is, we have to remember that z to the alpha is equal to e to the alpha log of z. So here we can see a formula where this log is a multiple valued function. Just before this one, we have solved this type of problems. So if we try to find the principal value of complex exponent, then z alpha will be e to the alpha natural log of z, but this time it is capital L. So L means this is defining the principal value of complex logarithm. And we know how to find this one. This can be found by setting n equals 0. So since we are dealing with log functions, we can think about the properties that we have. Let's have a look on the properties. If we have log of z1, z2, then we can write log of z1 plus log of z2. If we have log of z1 by z2, then we can write log of z1 negative log of z2. If we have log of z to the n, then we can write n log of z. We also know that log of e equals 1, where this log of e is defining the real logarithm. So if we have complex exponent z to the alpha, we can write this one as e to the alpha log z. For finding the principal value of complex exponent, we have to replace small l og by capital Log. That means we have to find the principal argument first, and we have to find the principal value of complex logarithm by setting n equals 0. So let's solve one problem. So just like exponential function, logarithmic function, this complex exponent has also some properties. So let's write these properties for our betterment. So we have, let's say, z to the alpha 1, z to the alpha 2. Z to the alpha 1 times z to the alpha 2. We can write z to the alpha 1 plus alpha 2. If we have z to the alpha power n, we can write z to the n alpha, where n is any integer. So these properties are helpful. So let's solve one problem from complex exponent. Let's evaluate 2I power 1 minus I. So we can compare with z power alpha. So this is z, this is alpha. So we are getting z equals 2I, alpha equals 1 negative I. So we know that if we have z to the alpha, we can write by definition e to the alpha log z. So e to the alpha log z. Now we can write z alpha, that is 2I power 1 minus I. We are just plugging the value. This is z, this is alpha. E to the alpha, that is 1 minus I log z. So log 2I. So we have to evaluate this. Let's say this is equation 1. So this can be found if we have log 2I. So we know how to find log 2I. That means now again the concept of complex logarithm is coming. We know that log of z equals natural log of r plus principal argument plus 2n pi I. So where n is 0 plus minus 1 plus minus 2 up to infinity. So z equals to I. That means we have to find the polar form of 2I. So we know that it is 0 plus 2I, that is the point is 0 comma 2. So 0 comma 2 is here. So r equals root over 0 is squared plus 2 is squared. So that means we have root over 4. That means 2. We have found r. Angle. That angle should be the principal argument. So since the point is in first quadrant, whenever I have started the session, I have mentioned that if a point is in first quadrant or fourth quadrant, then the formula that we have will give us accurate result. So y over 0, that is 2 over 0, so it is tan inverse of infinity, it is pi over 2. That means tan 90 degree equals undefined. So automatically we can see from this visual representation that it is 90 degree. So our principal argument has been found, it is pi over 2. So let's plug here. Log of z, that means log of 2i, equals natural log of r, natural log of 2. This is just acting as a real log, it is unique, plus argument. Argument is found to be pi by 2 plus 2n pi I. So this is our final result. We have found log of 2i. So from equation 1 we have e to the 1 minus I log 2i. We can now input this. It is natural log of 2 plus pi over 2 plus 2n pi I. So this is what 2i power 1 minus I is. So we have found our result. This is a multiple valued function because n is 0, plus minus 1, plus minus 2, and so on. That means for n equals 0, we will get branch. For n equals 1, we will get another branch. For n equals 2, we will get another branch. That means we are getting single valued function every time. All these are forming multiple valued function. So here, the same problem can be in a different form. Evaluate 2i power 1 minus I. But if I ask evaluate the principal value of this number, then at that time, besides this, we have to think like another way, e to the 1 minus I capital L O G of 2i. So let's say this is equation 2. So it means we are finding the principal value of the complex exponent, this one. So we know that from small l, if we need to have capital L, then we need to input n equals 0. So if n equals 0, then small l will become capital L. That is, complex logarithm will become single valued function, will become the principal value of complex logarithm. So it is log 2 plus pi over 2, this is 0, I. So from equation 1, we have found the complex exponent. But for principal value of complex exponent, we have equation 2. That means these two equations are same, but we are writing in different way. It is the general form and it is a specific form. So our result will be fulfilled if we write e to the 1 minus I log of 2I. So this log is coming from this one. It is natural log of 2 plus pi by 2 I. So this is the principal value of this complex exponent. We can say this is a function f of z equals this one. Now, if we want, we can also find our numerical value, because any complex function w equals f of z can be written in u plus vi form. Okay, for this problem, let's find the numerical value. Then it will be easier for you to understand. So 2i 1 negative I equals, we are evaluating the principal value of this exponent. That's why we are working with this equation, not this one. We can also work with this equation if we want. But let's say we are working with this. And we will reach to a numerical value. So e to the 1 minus I natural log of 2 plus pi over 2 I. So what we can write now? We can write e to the 1 negative I log 2 plus 1 negative I pi over 2I. Now we can multiply, that is, it is log 2 minus I log 2 plus pi over 2I minus I squared. So I squared is negative 1. So we are getting positive pi over 2. So 2I power 1 minus I equals e to the log 2 plus pi by 2. We are collecting the real parts and imaginary parts, plus I pi by 2 minus log 2. So now we know that e to the z1 plus z2 I can be written as in this way. Now we can see it is e to the log 2 plus pi over 2 e to the I theta, that is cosine theta, plus I sine theta. So we can also write in u plus vi form. We can multiply this quantity with this e to the log 2 plus pi over 2 times cos pi over 2 negative log 2 plus I e to the log 2 plus pi over 2 sine pi over 2 negative log 2. So this is our numerical value of this. That means we have found the principal value of this complex exponent 2i power 1 minus I. So we can use calculator to get this numerical value. It is now in u plus iv form, and this is f of z. So if we use calculator, then Let me use my calculator. This part is becoming 6.1474 plus I 7.4008. So this is done. We have found this result. So just like logarithmic function, we can think about complex exponential function. So complex exponential function is multi-valued function. From here we will get different branches. So branch 1, branch 2, let's say this is W1, W2, W3. So out of all these branches, the first branch is known as principal branch because it is found from n equals 0, then n equals 1, then n equals 2. So any z to the alpha can be written in this form: e to the alpha, either log z or capital Log of z. So just like logarithmic function, we can think about this function will be analytic, this multiple valued function will be analytic. If we take any branch, that branch will be single valued. So we are not going into details in the derivative and Cauchy-Riemann equations. Let's write directly. ddz of z alpha. We know that ddz of e to the alpha log z, let's say it is capital Log, because this capital Log is an analytic function we have shown already. So now we have to differentiate this. We know z to the power alpha is this one. So ddz of e to the z, we know it is e to the z. But we can remember chain rule from our differential calculus. So instead of z, if we have e to the 2z, that means what we can write? At first, we can think that we have only z. That means we can consider 2z as z. So formula is same. Differentiation of e to the power z is e to the z. Similarly, it will be e to the 2z equals e to the 2z. But since we have considered this one as z, we have to differentiate this again. So e to the 2z, differentiation of 2z is 2. Finally, 2 e to the 2z is the differentiation of this function. So similarly, we have to apply chain rule here. That means we can think about this is z. So differentiation of e to the z is e to the z. Since we have considered this one as z, this should be in differentiation form. So alpha is a constant. We know that if we have any constant, that can be pulled out. So e to the alpha log z, this alpha is pulled out. Now we have ddz of log z. And just before this problem, we have established that ddz of log z is 1 over z. So we can write alpha e to the alpha log z 1 over z. So this is ddz of z alpha. That means we can also simplify if we want. Already our differentiation part is over. We can keep our answer here, but we can also simplify if we want. We know that e to the alpha log z, e to the alpha log z is z to the alpha. So why not we write this one? Because z to the alpha can be written as e to the alpha log z. We can write. So we have this z in denominator. So alpha z alpha negative 1, because here we have 1. So that means we can relate to our differential calculus. ddx of x to the n is an x power n minus 1. Similarly, here we can establish ddz of z to the alpha is alpha z to the alpha minus 1. So this is done. So we have discussed complex exponents. Let's talk about complex trigonometric and hyperbolic functions. So these two functions are single valued function. Complex trig functions. So complex trigonometric functions are sine z, cos z, tangent of z, cotangent of z, secant of z, cosecant of z, sine, cosine, tangent, cotangent, secant, cosecant. We can say this is f of z, or w equals f of z, f of z equals this, f of z equals this, f of z equals this one, and so on. So that means complex trigonometric functions are defined just like real trigonometric function, sine x, cosine x, like that. So we have to understand the definition of sine z, cosine z first. So complex trigonometric function sine z is equal to e to the iz minus e to the minus iz by 2i. So this is the formula for sine z we have to remember. Formula for cosine z, e to the iz plus e to the minus iz by 2. So using these two formulas, we can establish all formulas. Suppose we have tan of z. We know that it is sine of z over cosine of z. Then sine of z is this one, cosine of z is this one. We can evaluate easily. Similarly, cotangent of z will be cosine of z over sine of z. Similarly, secant of z will be 1 over cosine z. Similarly, cosecant of z will be 1 over sine of z. So I have mentioned that complex trigonometric functions are single valued functions. So let's check. Suppose we need to evaluate cosine of I, which will be w equals f of z. So our target is to evaluate this. So we know that cosine z equals e to the iz plus e to the minus iz by 2. That means we are going to evaluate cosine z, where z equals I. So cosine z equals this. Let's plug cosine I. So where we have z, we are just plugging I. So e to the I times I plus e to the minus I times I over 2. So we have e to the I squared plus e to the minus I squared over 2. We have e to the minus 1 plus e to the minus 1 over 2. So it is e to the minus 1 plus e to the 1 over 2. So this is cosine of I. So we can see that we have only a single value on the right side. So that's why cosine z or sine z or any trigonometric functions which are complex trigonometric functions can be single valued function. So if we want, we can also find the numerical value of this. So e to the minus 1 plus e to the 1 over 2, it will be 1.5431. This is cosine I. So just like the previous problem, we are going to evaluate tangent of pi negative 2I. So we know that tangent of z, that is equal to sine of z over cosine of z. So this function will again be a single valued because any complex trigonometric functions are single valued. So from here we have to find sine of z over cosine of z. That means we can apply the formula of sine z and cosine z. We know that sine z is e to the iz minus e to the minus iz over 2I, e to the iz plus e to the minus iz over 2. So let us do some simplifications here so that it becomes a nice equation. So e to the iz negative iz over 2I times 2 over e to the iz plus e to the minus iz. So 2 and 2 can be cancelled. We have e to the iz plus e to the minus iz times I e to the iz minus e to the minus iz. So now this is tan of z. We can input z as pi negative 2I. So let's input tan of pi negative 2I e to the I pi negative 2I negative e to the minus I pi negative 2I over e to the I pi negative 2i plus e to the minus I pi negative 2i. We have also I here. So if we keep our result here, that is okay. Or we can also simplify to the numerical value. So this is up to us. But the main thing is on the right side, we have a single valued function. So complex trigonometric functions are analytic because these are single valued function. So we can say that we can find the derivative of sine z, we can find the derivative of cosine z. So let's have a look how we can find the derivative of sine z. We know that sine z is e to the iz minus e to the minus iz over 2i. So here 1 over 2i is constant, so we can pull this before. We have e to the iz negative e to the minus iz. Now we can see we have 1 over 2i. So derivative of e to the z, that is e to the z. By using the concept of chain rule for evaluating this, so what we can do, we can write it is e to the iz and derivative of iz again. So e to the iz, I is constant, derivative of z is 1. So we have I e to the iz. So that means I e to the iz negative. Similarly, dz of e to the minus iz will be dz of e to the z will be e to the z. We are considering this one as z. And again, we are differentiating this. So we have e to the minus differentiation of z is 1 and minus I is taken before since it is constant. So derivative of this will be minus I e to the minus iz. So that means 2i I e to the iz minus minus plus I e to the minus iz. And now we can take I before. So we have e to the iz plus e to the minus iz over 2i. So dz of sine z equals this. Now we know that e to the iz plus e to the minus iz by 2. This is equal to cosine of z. So we can prove ddz of sine z is cosine z. Just like ddx of sine x equals cosine x, we can say ddz of sine z is cosine z. But the proof is different. The proof is coming from analytic function e to the z. Similarly, we can show ddz of cosine z equals minus sine z. So we can also say ddz of tangent of z is secant squared z. Dz of cotangent of z is minus cosecant squared of z. Dz of secant z is secant z tan z. Dz of cosecant z is negative cosecant z cotangent of z. So this is what we know as complex trigonometric functions. Let's talk about complex hyperbolic function. So complex hyperbolic functions are also single valued. It will be hyperbolic sine of z, hyperbolic cosine of z, hyperbolic tangent of z. So all these are f of z. We can also think about f of z equals hyperbolic cotangent of z, f of z equals hyperbolic secant of z, f of z equals hyperbolic cosecant of z. Just like trigonometric function sine z, we can think about hyperbolic sine of z. So this is equal to e to the z negative e to the minus z over 2. So we have to remember this formula. Hyperbolic cosine of z is equal to e to the z plus e to the minus z over 2. So if we know these two formulas, then we can easily find the other ones. If we differentiate hyperbolic of sine z, we will get hyperbolic cosine z. If we differentiate hyperbolic of cosine z, we will get hyperbolic of sine z. But don't be confused with differentiation of cosine z is negative sine z. But differentiation of hyperbolic cosine of z is positive sine z. So this is important. Similarly, derivative of hyperbolic of tangent of z is hyperbolic secant squared z. We can also write d dz of hyperbolic cotangent of z, that is negative hyperbolic cosecant squared of z. Derivative of hyperbolic secant z is negative hyperbolic of secant z, hyperbolic of tan z. d dz of cosecant hyperbolic of z, that is negative cosecant hyperbolic of z, hyperbolic of cot z. So these are the formulas that we have to know from complex hyperbolic functions. So I have mentioned that complex hyperbolic functions are also single valued. So let's have a look how these are single valued. That means we will find only one output. Let's say we are going to evaluate hyperbolic cosine of pi I. So we know that hyperbolic of cosine z, that is e to the z plus e to the minus z over 2. So let's input z equals pi I. So we have e to the pi I plus e to the minus pi I over 2. So where we have z, we have plugged pi I. So we can see that on the right side we have only one value. We can find the numerical value also, that is e to the I pi plus e to the minus I pi. I have just rearranged this. So now we know that e to the I theta, that is cosine theta plus I sine theta. E to the minus I theta, that is cosine theta minus I sine theta. So cosine 180 degree that is equal to -1. Sine 180 degree is 0. Again, cosine 180 degree is -1. Sine 180 degree 0. So we have finally -2 over 2. That means we are getting -1. That means cosine hyperbolic of pi I equals -1. Hyperbolic cosine of pi I is equal to -1. So this is single valued function. So we have discussed all these elementary functions. The important one is complex exponential, complex logarithm, complex exponent, these three. Complex exponent and complex logarithm are multiple valued function. That means we will have branch point, branch cut. Let's have a look on some examples so that you can understand the pattern of finding branch point. So I have mentioned that whenever we have log of z, we can think about log of z minus 0. That means we can think about log of z minus a. So if we have log of z or log of z minus 0, then the branch point will be z equals 0. If we have log of z minus a, then the branch point will be z equals a. So let's have a look on some examples. So other than complex exponential function, logarithmic function, trigonometric function, complex exponents, we can think about some other function. Let's say f of z equals square root of z negative 5. How can we find the branch point of this? So we can consider just like z negative a. So z negative a, z negative 5. If we solve z negative 5 equals 0, so we will have z equals 5. So z equals 5 will be the branch point of f of z. Let's have another example. Suppose we have f of z equals natural log of z. What will be the branch point? We can think like it is z negative 0. So that means z negative 0 equals 0. So z equals 0 will be the branch point. Let's take another example. What will be the branch point of this? So this time we have to do a simple calculation. We can understand that it can be written as z squared negative 1 squared. So natural log of z plus 1, z minus 1. So we can write log a times b, that is log a plus log b. So here we can see that we have z negative a. That means if we solve this one for 0 and if we solve this one for 0, so we are getting z equals negative 1, z equals positive 1. So this time we have two branch points. Similarly, let's take another example. Natural log of z negative 1 over z plus 1. We have to find the branch points. So we know that log a by b is log a negative log b. So this is z negative a. That means we can solve this one. So it is z equals 1. This is z negative a. So if we solve for 0, we will get z equals negative 1. That means this time we have two branch points. So this is how we can find branch points. So whatever functions I have discussed here, all these are elementary functions. I hope you have understood all the concepts. So thank you.